Oh, yeah. Okay, so I think YouTube is running. Welcome to the afternoon session. And the first speaker is Max Wiesner, who's going to tell us about exploring the interior of N=1 field spaces. Thanks, Max.
Thank you very much. And thanks for coming back after the nice lunch. And thanks to the organizer for setting up this very nice workshop here in beautiful Saclay. And I want to talk about some recent work or stuff that I've been working on last year. This is loosely based on a paper that I put out last year around the same time, and some work in progress that maybe gives to some extent my perspective on some of the questions that were discussed actually in the previous discussion session. So since this is work in progress, it's not entirely polished yet, but since this is also a workshop, I thought maybe this is actually a good place to talk about this. So the idea is that I want to explore a little bit the interior of N=1 field spaces, where, as we just heard as we discussed in the discussion session, not much is known when it comes to actually genuine N=1 effects, like how to compute them, what is the structure of the field space in the interior, what is actually the nature of the theories there. So we know that in string theory and also in compactifications, these come often with a number of scalar fields whose vacuum expectation value determine the properties of the effective theory. So the values of the coupling masses of states or value of the EFT cutoff, you name it. And oftentimes we know, so then all families of the EFTs are then parameterized by the values of the scalar fields. And so we get a scalar field space where we have different, for example, perturbative descriptions where we actually have a good understanding of what is this theory, what are the properties of the theories, and the general structure of the field space gives us information about the general properties. For instance, duality frames, we use them a lot in highly supersymmetric cases to infer all our web of dualities, that we know different sectors, different perturbative regimes are actually part of the same modular space. So what do we know about the structure of M? I mean, it comes oftentimes equipped with some kind of metric which can be computed in perturbative limit of the theory, for example, in perturbative string theory regimes. And for example, in the case of perturbative supersymmetric string theory, which could be one of these perturbative phases where we actually know what to do, one can match this with expectation from gravity and obtain a metric in these perturbative phases. And then if we have enough supersymmetry, actually we sometimes know the entire structure, we know the metric everywhere because just the structure of just the supersymmetry algebra gives us enough information, and the metric can be evaluated at any point in modular space. With less supersymmetry, the situation becomes way more difficult, but sometimes we can rely on non-renormalization theorems that allow us to actually interpolate from such a perturbative phase all through the modular space that I didn't draw here. An example of this is, of course, 4D N=2, which we love and which I think we understand very, very good, because at least here the modular space factorizes into a vector and hypermultiplet sector. And depending on which actual theory we look at, only one vector contains the string coupling, such that the other one is actually tree-level exact, which we know, for example, in type 2 Calabi-Yau compactification, this would be the vector sector. And heterotic on K3 times D2, this would be the hypersector. So but the question is, what about the more realistic cases in 4D with minimal or no supersymmetry? I'm here a bit more modest, and I want to talk about minimal. But before we go there, let's make some warm-up. What do we actually know in type 2A Calabi-Yau compactification of theories that still have N=2 supersymmetry? Where we draw also, as we discussed or as was discussed in the discussion session, we draw a lot of our intuition from, for example, from the vector multiplet sector of type 2A. So let's first gather some intuition from there, specifically focusing here on type 2A compactification Calabi-Yau. So we know here that the modular space factorizes in a hypermultiplet sector, which is spanned by the type 2 dilaton plus axionic partners in the complex structure of the Calabi-Yau X3 plus axionic partner. And the complexified Kähler moduli gives us the vector multiplet sector. Now the N=2 supersymmetry ensures actually the factorization between these, such that we know that the vector multiplet moduli space is tree-level exact, and we can trust the structure that we can derive from a string worldsheet, for example, using mirror symmetry to relate the complexified Kähler moduli space to the complex structure moduli of space of X tilde of the mirror, where we actually have everything classicalizes, and we can just compute our periods in different limits and obtain trustable results. So thanks to the factorization, we can also do this map to the mirror symmetries mirror symmetric complex structure moduli space of X tilde. We can actually, this allows us to also describe the small volume regime of the Kähler moduli space of type 2A, which is what we use very often. And we can, for example, infer the singularity structure just from the mirror. So you have here two, in this example, this is just a sketch. We have two moduli. Here we would have a Calabi-Yau phase, and we know that if we go to small volumes, we could get other phases that are not necessarily described by a Calabi-Yau, but by some hybrid phase, by some Landau-Ginzburg phase, or some orbifold phase. So this is the picture that we know and we love. We know how to describe type 2A, the type 2A vector multiplet modular space. And since this is tree-level exact, we can actually also infer what is going on in the small volume limit, where we can still trust our field theory, CFT description, though not necessarily the geometric one. But so, okay, what remains of this picture if we actually go to an n equal to 1, genuine n equal to 1 theory? And what I want to focus here, even though maybe somebody would say, why would I do it and look at F theory? I take the stance, okay, F theory teaches us a lot. It gives us a genuine n equal to 1 theory. So I look at F theory on elliptically fibered Calabi of 4 folds. So some elliptic fiber over some base B3. The scalar field space then is spanned by the complex structure model of X4 and the complexified volumes of devices in B3. And we know that in the large volume regime, if we make the base B3 very large, all the supersymmetry breaking effects that come basically from the non-trivial fibration of the torus over B3 just become very dilute. It's almost a constant vibration. So all the supersymmetry breaking effects are diluted because we can think of B3 actually that it plays the role of the 4D dilaton. So we get a very weakly coupled theory. And in this limit, the moduli space is described by just a factorized, it just factorizes between the complex structure sector and the Kähler sector. And this is what oftentimes is a starting point to actually investigate what is happening in F theory. But so the question is, what happens actually away from the overall large volume limit? So what happens if we do not dilute infinitely much the supersymmetry breaking effects? So what happens, for example, in the small curve limit for some curves in B3, where we in type 2A, we somehow on Calabi or threefold, we know what is happening thanks to mirror symmetry, and we can somehow infer the structure there. And what about actually the mixing between complex structure and Kähler sector that I think Eric also in one of his questions raised? I don't know where Eric is, but so let's first understand to get an intuition what could be the structure of the Kähler field space in a genuine n equal to 1 theory. So we consider first small volume limits in B3. So naively, one might expect a similar pattern as in type 2A. We have shrinking genus 0 curves, which for type 2A fall in these three classes, which are either these flop curves, where only a curve shrinks when we shrink, and we can trust actually the classical geometric picture. Or we have this gauge enhancement points, where divisor shrinks to a curve, but we have locally enhanced supersymmetry, such that we can still trust the classical geometry. Or divisor shrinks to a point where we then actually enter an orbifold phase, and we know that our Calabi-Yau phase needs to end eventually. So for F theory on an elliptically fibered Calabi-Yau fourfold, this can at best be true for curves that do not intersect the anticanonical divisor K-bar. So curves that basically do not see the breaking of supersymmetry, or one might call them curves that are actually n equal to true. But of course, the interesting case is now not this, because there it won't be sensitive to any genuine n equal to 1 breaking effects, n equal to 2 to n equal to 1 breaking effects. But the interesting case is what happens if we shrink a curve C such that it has a non-zero intersection with K1. Can we trust the classical geometric picture and the Kähler potential derived from it? And therefore, let's focus on these curves. Let's first say, okay, what happens if we intersect this curve once by K-bar? Then these are the possible normal bundles, and we take the first case and ask, can the geometric description still be trusted? So we look at one can look at the corrections to the effective action. And we therefore first show that a curve with such a normal bundle, there needs to exist a divisor D whose volume is linear in this modulus, or in the volume of the curve BC. So it necessarily also shrinks in the limit that we shrink this curve. Of course, now this volume, or actually what would be correctly the D3 brane instanton action receives corrections alpha order alpha prime squared as computed in a series of papers in the 2010s. So these are the kind of corrections which depend on the topological data of the fourfold. So this is just the classical volume which goes to 0 as we shrink the volume. Then we have some correction that are suppressed if we we make the curve small, but we're still at large overall volume. And this would be the relevant correction. So here I have it again. So the question is, of course, if this correction is there, then we see, okay, actually our classical geometric picture breaks down because this correction becomes large and becomes way larger than the classical regime. So does this coefficient vanish for a curve which satisfies this? One can consider, for example, smooth Weierstrass models, which are just over a base that is in itself rational fiber, just to get some intuition. And one can compute this correction and sees that it's precisely proportional to the intersection between the anti-canonical class and C. Hence, it does not vanish in the case this is non-zero or even 1. So it dominates over the classical term. So we cannot trust just the classical field space geometry for such a curve that intersects the K-bar, and actually the corrections take over. As a consistency check, we see if we have a curve that is actually what one might call an n equal to 2 curve, this correction vanishes identically because this is 0. And we can still trust the geometric picture because basically this curve does not see this genuine n equal to 2 to n equal to 1 breaking. Another example could be if we intersect this twice and we take this normal bundle, which means that C is actually fibered by a rationally fibered over some base B2, where we have a dual heterotic string theory, which of course was already shown here, but then in the context of the weak gravity conjecture used again and analyzed in detail in this paper. And so what happens here if in the limit of small c at constant overall volume, we again get that all devices, irrespectively of whether they contain C or not, they actually get in the correct limit where we keep this constant. They get a correction which diverges in the limit. And one can now use the duality actually to the heterotic string, exploit this, at least in and show that at least in simple examples, which is what I did here, there's a strong coupling singularity which is reached for a gauge theory on a device at D that is the base, or this is the 0 section of this rationally fibered B3. So this guy should vanish at least up to this order in perturbation theory at the singularity. And one sees that all vertical devices with respect to this fibration should have a minimal quantum volume, which one can just write like this, where I want to highlight that there is a slight dependency on the complex structure parameter of X4, which one can actually infer via this duality. So we see that actually that here we reach a strong coupling singularity that you would not have seen from the n equal to 2 parents, or like if you would just apply n equal to 2 logic. And we see a mild mixing between the complex structure parameter of X4 and the base B3. How do I do with time? Okay. So we get a strong coupling singularity at finite distance and a mixing between the complex structure and the Kähler sector, which means that really we should not view this necessarily as two separate sets, but we, as Ilarion said, we have just one pack of moduli in the n equal to 1 theory, and dividing these by what comes from complex structure and Kähler sector is a bit arbitrary. So we see that the n equal to 1 theory we have significantly different from the n equal to 2 counterpart, so we cannot just view it as n equal to 2 plus small corrections, because then we would have not seen this effect. In general, the field space geometry for small genuine n equal to 1 curves is hence not describable by the classical geometry that we just inherit from the Calabi-Yau geometry because of these important corrections. The corrections are big, and the field space does not necessarily factorize anymore. So, but let's say, okay, we go away from this small curve limit, from this very small curve limit, where we would say, okay, if I make a curve that is intersected by the 7 brands, make this very small, then I would also expect the n equal to 1 effects to blow up. Can I still trust the classical field space structure? So can I still think about this as some factorized, just because somehow there's still some protection from supersymmetry? Or does this really just break down for very small volumes? Or are also corrections important at larger volume, or for example, if I go to large complex structure? And so So one might expect that indeed this mixing between scalar and complex structure is sufficiently suppressed as long as all the divisor volumes are very large. So this would be some picture like this would emerge. So we have here the inverse divisor volume. If this is very large, and here we have the complex structure sector, we can just treat this effectively as the complex structure field space with the scalar potential just coming from the period geometry. Oops, sorry. And this is oftentimes motivated by viewing F-theory via type 2B orientifolds, because in type 2B Calabi-Yau compactification, the complex structure sector is classically exact, so it should not, we can just describe it through this scalar potential. And one could evaluate the periods of X4 reliably to infer the structure of MCS if one wants to work with actual F-theory. And the periods integral, of course, simplify close to boundaries of the complex structure sector, which I would, for instance, put here. This would be, for example, my large complex structure point, or any other of the points that Irene and Thomas classified in detail. So this is typically the setting in which one searches for flux vacuosurfs, assuming this factorization. But the question is this picture correct? Therefore, consider a very simple example. It's a very simple example of a Calabi-Yau fourfold. That is an elliptically Calabi-Yau threefold times T2. So our base B3 is just B2 times T2. So F-theory on X4 now leads to a four-dimensional theory with n equal to 2 supersymmetry, but I would not immediately view this as some kind of orientifold. So question, can we already see in this theory what to expect for, this should be a 4, the mixing between complex structure sector and the oval volume modulus? Therefore, in this n equal to 2 thing, we have a factorization between vector and hypermultiplet sector, which is now, the hypermultiplets are now the complex structure moduli of this Calabi-Yau threefold that is upstairs here, and an oval volume B2 plus axiomic partners. And the scalar moduli of B2 and the moduli of T2 are just in the vector. So this theory is, of course, just dual to type 2A on T2 on the same Calabi-Yau threefold. And we can identify the moduli space via a simple map where we identify the complex structure moduli on both sides, and the overall volume modulus of B2 is identified with the 40 dilaton. But we now know that the type 2A hypermultiplet sector receives correction due to the D2-brane instantons, and actually which are not necessarily suppressed if we go to certain limits. These D2-brane instantons contribution to the moduli space metric have actually been computed in a series of papers here, and I think it started initially with the mirror dual. So we have that the 40 dilaton is the classical one plus a bunch of D2-brane instantons. And in particular, in the large complex structure moduli, in the large complex structure limit, actually the mirror of that, we investigated in this paper in 2019 what is the consequence of this. Or if you actually want to work in type 2A, you should look at this paper by Raphael, Daniel, and Timo. And the effect of this instanton is that they effectively obstruct large complex structure limit at finite value for the dilaton. So we can now break supersymmetry to n equal to 1, for example, through a non-trivial fibration over some P1. And then, of course, at least classically would expect that the complex structure sector of X3 is part of the oval complex structure sector. And the expectation is also that the corrections that are present already in n equal to 2 should not suddenly disappear if we break to n equal to 1. So this would mean that asymptotic regions in the complex structure sector of X4 also receive corrections at finite volume of the B2, which is now the fiber of B2, due to corrections to what I would now interpret again as the D3-brane instantons on the divisor that is just the fibril divisor, which previously was just the base of the Calabi-Yau. So we get also some kind of corrections that now depend on the complex structure moduli in the limit. And actually, you can see in simple smooth Weierstrass models that there is again this C1B3 squared, which tells us, okay, actually, if I have a non-trivial fibration for this Calabi-Yau, these guys contribute. So this guy goes actually, because this is just the same as the effect of the D2 instanton, goes to infinity close to the borders or boundaries actually of the complex structure sector of X4, or better to say the subspace of it. And so the consequence is that we can never treat X4 as decoupled from sector unless we are actually at full infinite distance limit. So this, yeah? No, it's not necessary. It's already in n equal to 2. It's not a holomorphic redefinition. Yes, exactly. So the consequence is that actually this picture that I drew before is not quite correct. But actually these corrections become relevant unless I take like a double scaling limit, where I first go to large volume and then to large complex structure. So this is one of the upshots. So this is still work in progress, and this is a workshop, so we might discuss. So the conclusion is I wanted to explore the interior of the n equal to 1 field space and see, okay, where do genuine n equal to 1 effects, where do they come from? Can we at least somehow compute them using dualities? And how do they affect the structure of the field space? I focused. I wanted to stress that we can only use the n equal to 1 to intuition if the breaking effects are infinitely diluted. So if we go to large volume, for example, viewing the complex structure sector as embedded in the full moduli space, that this is just possible at infinite volume is very reminiscent of how the vector multiplet sector of type 2b is embedded via the CMAP in the hypermultiplet sector in type 2a. And otherwise, we expect that the n equal to 1 breaking effects are actually important. I explicitly considered F0 compactifications on fourfolds, where I first showed that the n equal to 1 effects become large if I actually have n equal to 1 curves. And that the mixing between the Kähler structure and complex structure sector and Kähler sector become important away from this large volume limit. And in particular, asymptotic regions in the complex structure sector only describable through the classical geometry in this double scaling limit, which is basically the same that we observed with Fernando and Florent in the n equal to 2 hypermultiplet sector. But of course, these are still very special cases. So a question is what happens in general n equal to 1 cases, and what can we say there? So this is the work in progress. Thank you very much.
Thank you, Max. Questions?
I'm just trying to sort of get a geometrical picture. When these large corrections appear in the curved strings, what happens geometrically? Is it
Hold the cube.
Is it some wrapped brain? Is it the curvature becomes large? Or what happens?
In which?
In the case, in this one case that you mentioned just on the previous slide, the curved strings, which intersects the canonical divide.
Yeah, I mean, you have like the topology tells you, or like the topological information tells you that you automatically also shrink an effective device. So you in F theory, which I don't know how to see this actually directly from type 2.
Yeah, and then what happens?
This is you just get a bunch of corrections.
Small.
So sorry?
No.
So I was just wondering, do you have any?
I would say I don't have a geometric interpretation then. In the same way that if you go to a Landau-Ginzburg phase in type 2A string theory, you don't necessarily have a geometric interpretation.
But sometimes there's one in terms of wrapped brains, or you can see something going wrong, like the curvature becomes large or things like that.
I guess that is what is happening, because you saw this effects that are proportional to C3 time wedge J, and if that becomes larger than the classical curvature, then okay, this is precisely what's happening.
Yeah. If you ask a question, hold the cube and it will record or something. Yeah.
It's very naive. This dilution in the infinite volume limit, that's usual decoupling between closed and open strings. That is what it's about.
Right. Yeah. I would say at least in F0, the large volume limit is where basically your vibration becomes infinitely adiabatic, and so hardly changes, so you're supersymmetric.
Right, because the n equal 1 means that you integrate in open string modes which form n equal 1 multiplets, so you want them to decouple essentially. Otherwise, I mean, there's no talk about n equal 2, right?
Yes,
I mean, that's the only way I can understand
it. You basically get a triggered vibration, right? Where you would say, okay, the open string sector decouples.
Yeah.
Okay. That's interesting.
More questions? Irina.
This is fun.
If you can.
Yeah, so you get that thanks for the talk. You get that the corrections become more important as you go to the boundaries of the complex structure moduli space, unless you have this double limit that you take the volume going to infinity first. But so you explain how it works, but can you repeat, like, what is intuition? Why the corrections become more important as you go?
So my intuition that comes from the hypermultiplet sector. Because
Yeah.
if you go in the hypermultiplet sector of type 2A on this, I mean, there you have the two-brain instantons that just this action just becomes smaller and smaller, which is just the C map of what you saw with Aaron and Thomas, right? That instead of the three brains on cycles that become massless in the large complex structures, you now have two-brain instantons becomes, right? There's also a paper by Thomas and Damian where they analyze this. So these become more and more important in the same way you get in the C dual vector multiplet modular space, you get more and more light states. So they just translate via the CMAP to this kind of correction.
Okay, and then bodies that this should happen in all boundaries because we always have some
Exactly.
massless ones. I see. Yeah. Okay.
So it's as long as you are, I think this infinite distance boundary, I don't actually know what happens. But at the conical, we also know that the metric gets corrected thanks to Uhuru Iwata, right? Because they calculated this and they say, okay, actually, there's no singularity anymore because of these and I would expect this to be happening.
There was another question over here and then over there. Yeah.
Okay.
Can I ask a quick question? Yeah, thanks for the very nice talk. I was curious about the correction that you computed to the divisor volume. Say that you have a 77 brain wrapped on that divisor for which you computed the correction. Are you computing the holomorphic correction to the holomorphic gauge coupling, or are you computing the correction to the physical gauge coupling? The reason why physical, then like, can I just interpret it as after computation of the Kaplinovsky-Louis formula, because it looks awfully similar to that. Like basically, yeah.
Like if you for Kaplinovsky, if you compare to the heterotic string, for example, and you look at certain devices that are actually the ones that host the D7 brains, then in this paper with Timo and Daniel and Sonju from like 3 years ago, we actually matched these to heterotic loop correction. But in general, I'm not sure if these are, like if you don't wrap a 7 brain, then there's no heterotic, then there's no interpretation as
right, but you can still like imagine like there, even if you are computing the correction to the D-instant amplitude or you can assume that like there is a fiducial D-brain or whatever, and then try to compute like Kaplinovsky-Louis, right?
But yeah, so at least in the heterotic dual, that's actually one of the things that we used in the paper with Timo and Daniel and Sonju. We actually matched it with the.
That's great.
So because there you see that actually, if you want to match with Kaplinovsky-Louis, there are two contributions. One half of them are already in the classical F0 geometry. The other one come in order alpha prime squared. So yes is, I guess, the answer to your question.
Oh, great. Thanks a lot.
Yeah, maybe one more quick question.
Hi, thanks for the nice talk. So let's say I have like an F-theory realization of a 61,0 SCFT on a general Riemann surface.
Yes.
In that case, my base obviously is infinite volume. Do I still expect a separation or a factorization of the complex in Kähler moduli?
I mean, you say 60 n equal to
61,0
on times T2, like on
times a general Riemann surface.
Times then I would still expect that because the only modulus that is mixing here is the overall volume of the base B2 of your F theory, right? And this modulus you don't have if you take a non-compact.
I see, but the elliptic fibration is no longer like it's not locally trivial still, even though I took the base volume to be infinite.
But now you're talking about the elliptic of Calabi-Yau 3 upstairs.
Sure. Yeah. Okay.
Let me just think.
Oh.
I have to think about it. So I was here now talking about the complex structure and the overall volume, which of course in that example you don't have. But
okay, thanks. Yeah, we can talk more.
Okay, let's thank Max again for a great talk. That's great. Okay. All right, so the next speaker is Nicola Cripiori, who's going to tell us about deconstructing scale separation with weak gravity and anisotropies. Thank you.
Okay, so first of all, let me thank the organizers. It's my pleasure to be here. And I was asked to talk about scale separation and was hoping to have some recent results, like in this period, but it didn't work out. So we'll talk about some results from this year, beginning of this year, and also from the past 2 years, more or less, done in collaboration with several people from various places. And let me start by remembering that Swampland conjectures, as we know, are a window into quantum gravity. The very fact that this conjecture exists or can be formulated is a proof of concept that quantum gravity is mixing UV and IR. And typically what you do is that you test conjectures from top down, so from string theory, because this is basically the best understood framework in which to work. And this is an extremely important job, because indeed is the only way we have at present to gain confidence in those conjectures. However, this is not what I'm going to do in the first part of this talk. In the first part, I will follow somehow a complementary approach, which is that I will use, or I will assume, certain conjectures to be true, so I will not question them at all. And then I will use them directly as tool to rule out certain properties. In particular, I will apply them to 4D and 5D supergravity, being agnostic about the possible UV completion of this theory, so to any possible supergravity. And I will show that you can say something about scale separation in Ante de Sitter, and also with some minor modifications, so with some small additional assumptions, you can also say something for de Sitter, but I will just be brief on de Sitter. I will mostly talk about scale separation. And for this approach to make sense, of course, you have to use conjectures which are tested and checked. And for this reason, we used the weak gravity conjecture, the magnetic version of the weak gravity conjecture, which is a statement on the ultraviolet cutoff of effective field theories, which is one of the most tested conjectures indeed. In the second part, instead, I will follow this more common top-down approach, and I will review some construction of scale-separated Ante de Sitter for vacua we did with many people here in the audience in type 2A supergravity. There are many features one could discuss about this construction. I will focus on one of them, mainly for reasons of time, which is the fact that you have to insist on the internal manifold to be non-isotropic. So you have to move away the ideal situation we usually study, in which the full manifold is isotropic. And then as a final question, maybe this can be a more general lesson, and okay, but I cannot say much more about this for the moment. So let me start on the first part, where I will use weak gravity conjecture to put constraints on scale separation. Actually, the very idea can be understood from a different and simpler setup, which has nothing to do with scale separation. But the very idea can be understood from just for d n equal to 1 supergravity with one vector multiplet. Now, in this model, you can do a simple deformation of the theory, still preserving supersymmetry of the action, but breaking it on the vacuum. This deformation is known as Fayet-Iliopoulos deformation. It means you introduce a parameter, psi, which is called Fayet-Iliopoulos parameter, which is generating a scalar potential. In this case, there are no scalar fields, so the scalar potential is just a constant. Now, there are various arguments why this psi has to be quantized. More in general, you can think of this as a charge, and one of the standard law of quantum gravity is that charge is quantized. So this is one assumption you will need, but not much more than this. Because once you assume that psi is quantized, essentially you don't have any freedom in tuning it to be arbitrarily small. So if you want to make this cosmological constant small, The only option is that you have to tune the gauge coupling to be small. So if you are interested in this limit, you are going essentially towards a limit of small gauge coupling, so towards a limit of restoration of a global symmetry, which in this case is one R symmetry. And this is telling us that something is bad, probably in this direction. Still, you might say that I'm not forced to look into this limit. I can just study the model away from this limit, and nothing is bad in that case. To say that indeed the model is bad always, you can use the weak gravity conjecture, because the weak gravity conjecture allows you to trade the gauge coupling for the cutoff, for the ultraviolet cutoff of whatever is your effective field theory. So you reach a statement that the cosmological constant scale is actually of the same order as the UV cutoff. You cannot decouple them because there is no other parameter you can use to decouple them. Meaning that in this case, you would conclude that this model is not protected against corrections. So this scale is a proxy for the IR cutoff in the sitter. So you are in a situation in which IR cutoff and UV cutoff are not decoupled. So there is no window really in which your effective field theory can live. So this, you would conclude that this is not a good effective field theory. And in general, pure Fayet-Iliopoulos terms are in the swampland. And the same conclusion, in fact, was reached with a different argument using absence of global symmetries, but not in this way, in another way, by Komagosky and Seiberg. And what we showed is that the weak gravity conjecture has this information somehow built in. Okay, so this has nothing to do with scale separation, but the point is that you can use it in other models to constrain scale separation in a very similar way. Actually, you can use it in all supergravities, all gauge supergravities with at least 8 supercharges. I will explain why I need 8 supercharges at least. And you can show that this relation parametrically cannot be satisfied. So this would be parametric scale separation. I cannot exclude to have a small amount of scale separation depending on what is small, but parametrically I can exclude this relation if the weak gravity conjecture. This is completely general. We not use assumptions beside the weak gravity conjecture here. You can do a similar work for the sitter, but I need one more assumption for the sitter. It's not automatic. And of course, as I was saying, there is one assumption underlying all of this, which is the fact that the weak gravity conjecture holds in ante the sitter or the sitter, so away from Minkowski, where it is originally formulated. And it holds in such a way that this relation is not modified drastically. So there can be corrections, which, for example, can be small when the radius of your space is of your ADS space is large. Of course, this is an open problem which I'm not going to solve. What is the correct formulation of the weak gravity conjecture away from Minkowski? I think it's not known at present. So as a working assumption, I would need to use this slightly away from Minkowski. But still, if we are in the supergravity regime, you expect that corrections suppressed with the ADS radius are small in this case. So you expect that probably this assumption can be meaningful. Okay, so here is a sketch in 2 slides how it works. If you wanted the precise derivation, is a bit more technical, so I didn't put it here. But this is the logic. And I'm doing here in generic notation for any gauge supergravity in 4 and 5 dimensions at least. The starting point is the vacuum energy. And it is a fact that in supergravity, in supersymmetric ante-de sitter vacua, the vacuum energy is always given by the gravitino mass or the trace of the gravitino mass matrix. So here is a completely general fact. Then you need 8 supercharges at least, because with 8 supercharges at least, you can trade the mass here, the gravitino mass, for some function of the gauge coupling. So you go from the gravitino mass sector essentially to the gauge coupling sector. And you cannot do this with 4 supercharges because you have a superpotential, and in general, this might not be true for a superpotential from a purely bottom-up perspective. In particular, for n equal to 2, so 8 supercharges in 4 and 5 dimensions, you have to use what is called special geometry or very special geometry. And it's not a big deal to work out the precise relation, and you can show it very explicitly. So you rewrite the vacuum energy in terms of the gauge coupling, but this is a generic gauge coupling of whatever the gauge group is. I'm doing this for any possible gauge group. So in principle, you are almost done, but you have to be a bit more refined in case you want to make sharp statements. So the question is, what is the gauge group? And this can be answered, actually, What is the form of the gauge group in the vacuum for supersymmetric anti-de Sitter vacua is known, and at least is known for the part we're interested in. So it is known that whatever the gauge group is, it breaks into two pieces. One piece is gauged by what is called the graviphoton, and another piece is this piece will be gauged by the other vector fields in the theory, and is model dependent. However, this piece gauged by the graviphoton is always there with at least a supercharger, is model independent, and it can be calculated. The generic form is this one. So for example, for n equal to 2, you will see that there is always a U1 factor. Otherwise, the group is bigger, but you can either argue with the Cartan subalgebra or assume that there is an unbroken E1 factor, which is typically the case if you look at the concrete model. So once you have understood the structure of the gauge group, you can just split the contribution into the graviphoton contribution plus whatever else is remaining, the matter contribution. Due to the properties of supersymmetry, there is really a plus sign here, so you can neglect this part, and you have an inequality of this kind. You take the absolute value and you impose the weak gravity conjecture, and essentially you derive the relation that the Hubble scale or the cosmological constant scale cannot be decoupled by from the UV cutoff. The reason is that whatever is here is a gauge coupling, is a whole thing which is a gauge coupling. You don't have any other parameter outside this function. So there is no other field or parameter here which I can tune. It's really a one-to-one relation between these two scales. And this then, from this you can conclude that if you believe the weak gravity conjecture in this way, there is no scale separation for this model. So let me give you an example very briefly. A known class of models from top down, which gives for the n equal to 2 gauge supergravity, is M theory on Sasaki-Einstein 7 manifold. To specify the theory, you have to tell me the pre-potential, which is a function of the scalar field here, and also the quaternionic metric, which is needed to understand the gauge sector, the gauging. You can understand that there is a U1 cross U1 gauging, which breaks down to U1 on the vacuum. So there is a U1 on the vacuum as expected. And you can work it out very explicitly. You can understand what are the moment maps of this U1. It will be a Payet-Iliopoulos gauging. And you can calculate the vacuum energy. You will see that indeed it's given by the product of the gauge coupling and the charge and the number. There is no other parameter entering this relation. So Q cannot be tuned small because it's a charge. And then the only way to have small, and then you essentially, G is the UV cutoff, so you cannot decouple again the UV cutoff from the cosmological constant. So what we would conclude is that these models are honest model in string compactification, but they are not good four-dimensional effective field theories. If you want to use them as four-dimensional effective field theories, you are in clash with the weak gravity conjecture. So the results we have is that we have an explicit argument for n equal to 2 and n equal to a supergravity in 4 and 5 dimensions. And we believe that there is no clear obstruction in going beyond. In particular, we don't see any clear obstruction in proving it for any number of supercharges in the between, and also in going beyond 5 dimensions. In fact, there are even proofs in step 2, for example, that supersymmetric anti-de Sitter 7 vacua cannot be scale separated. You can be a bit more brave. You can combine this with other conjectures. For example, those saying that non-supersymmetric anti-de Sitter vacua are unstable. And this will probably tell us that there are no really lower dimensional effective field theories in anti-de Sitter regardless of supersymmetry, but these are yet a further step. So what we learn from this is that the room, the only window which is still not covered, so where scale separation seems to be possible with respect to this logic, is the case in which we have only 4 or less supercharges, meaning 4d n equal to 1 or, for example, 3d n equal to 2 or less. And indeed, all known examples in the literature, in string compactification, are in this window. There are no other examples known, as far as I'm aware, in other regions. So before going into one of those examples, let me briefly tell you how you can modify this to say something for the Sitter. The starting point is always the vacuum energy, which now, however, has 2 contributions. One entering with a plus sign, which is breaking supersymmetry, and the other with a minus sign. due to this fact that there is this minus sign, in principle, I can tune this scale to be small by canceling one contribution against the other. So this is the way out for the argument I just gave you. The only way to proceed that we saw is that we had to assume that the gravitational mass is vanishing. So what we can say is that for the Sitter vacuum with vanishing gravitational mass, you just have the gauge coupling here, then you repeat the same trick, identify a factor of the gauge group, which you associate to the weak gravity conjecture, and then there is the rest. And then you play exactly the same algebra to derive the bound I showed at the beginning. So the IR cutoff is essentially of the same order as the UV cutoff. So these models are not protected against correction. So you might say that this assumption about vanishing gravitational mass is a bit exotic, but this is not, at least not in the supergravity literature. All the few known stable de Sitter vacua in n equal to 2 or bigger than supergravity in 4 dimensions have this property. So in 4 dimensions, we could rule out all non-stable vacua just in supergravity. In 5 dimensions, to our surprise, when we look into the literature, there are vacua which are stable, the Sitter 5 vacua just in supergravity, but don't have this property. So still, I think this is an interesting direction to be understood further, because for some reason you would expect that this model, by a dimensional reduction, will go down to this model, but it's not so straightforward. We seem to have different properties with respect to the weak gravity conjecture. And this is interesting to be investigated further also in light of this recent work connecting higher dimensional de Sitter to lower dimensional cosmic acceleration. Anyway, the message for de Sitter is that modulo the assumption on the gravitational mass, the most promising corner seems to be, again, a corner with very few supercharges at the Lagrangian level. And finally, before going to the top-down construction, what I showed you can be perhaps a hint of a more general lesson, which is the fact that somehow Swampland conjecture have a nice behavior. Yes? First derivative equal to 0. I'm not checking stability. No. I think there are examples, yes, but those are tachyonic, so we are mainly aiming at stable vacua. But I think there are also examples. I have to check again because it was 1 year ago. I don't remember the literature, but I think there are examples with 0 gravitational mass and the tachyonic direction. I can tell you later. I just have to check. Okay. No other questions? No. Okay. So I was saying that this perhaps is hinting at a more general picture that supergravity combined with Swampland conjecture is a useful tool in the sense that I showed you instances of this first line here. So supergravity plus weak gravity is essentially giving us statements which are the manifold of supergravity plus de Sitter conjecture. So I was excluding de Sitter vacua using another Swampland conjecture. And perhaps you can be a bit more brave and start from a known conjecture and try to predict a new one. Of course, this is much more challenging also if you really work just at the supergravity level, but this is an open possibility. Now, the second part, and in what is left, I will review a construction of a scale-separated class of vacua in type 2A, which was already mentioned this morning, but I will focus on some specific properties. Now, as we know, one of the most celebrated class of vacua is what is called DGKT after the authors of this paper, even though many other, this paper here, but many other people contributed to it during the years. And this model has some peculiar properties. So it is a massive type 2A compactification on manifold with symmetry structure, and those explains singularities. And there is a nice property, which is the fact that you have a parameter, a flux parameter, for flux in this case, which is not bounded, is not entering Bianchi identities. It can be arbitrarily large. This is a nice property per se, but what is remarkable about this class of models is that when this parameter is large, other remarkable things are happening. So the cosmological constant becomes small in magnitude. So you are going towards Minkowski essentially. and you are going in a regime of large internal volume and small string coupling. So you are more and more in a regime in which you can trust your supergravity computation. Of course, there are reasons of concerns which we have heard about this morning. One is that these are vacua in massive type 2A, which are somehow more difficult to understand geometrically from 11D perspective. And also, as Thomas was saying, you are in a situation, you find the solution in an approximation. So you don't find straight ahead the full solution, you find an approximated solution, which is called a smeared solution. And recently, it has been understood how to make progress along this direction. So in fact, both concerns can be addressed. This was one of the motivation of our work. The first concern was already somehow addressed in this paper. The idea was presented here, essentially, is to go to massless type 2A by appropriately choosing T-dualities. The second concern is the possible solution to the second concern is instead more recent, is to these people. And the idea is that you can set up, in this case, it's not always true, but in this case you can set up a systematic expansion because there is a parameter which is naturally small, which is again a power of this flux number. And then you just solve equations systematically order by order in this perturbation theory. So you can capture order by order, in principle, the correction to the smeared approximation. And what people did so far indeed is just the first order because the computation is demanding. But in principle, the tools are there. So we combined these two steps, and this led us to possible evidence for scale-separated vacua in massless type 2A. It actually both have weak and strong coupling, meaning that also this vacua could be also vacua in empty. The setup is the following. You have what is called the Nivagasava manifold, which is essentially a special subcase of a twisted torus. And what is important that I'm going to stress less is that you can think of this T6 as 3 copies of two torus, so we have 3 tori. And the general solution was, smeared solution was already known. We computed the first order correction in the back reaction to this solution. But before doing so, we actually perform a generic scaling analysis. So we asked ourselves which scaling freedom we have in the parameters, in the size of this tori to play with. And this turned out to be crucial for this model because, first of all, a fairly general scaling class is this one. There are 3 parameters, A, B, C, which are arbitrary, modulo some conditions for consistency, but they're basically arbitrary. And then once you are here, you can just tune your A and B, C and ask for your favorite properties. You can tune A, B, C and ask for scale separation. And if you do it, you will see that if you insist on an isotropic manifold, so all radii to be equal, you don't find scale separation. So if you would have naively started from an isotropic case without performing the scaling analysis, you would have concluded that this class of vacua has no scale separation. You have missed this possibility. Instead, you can choose the 3 tori to be different. So what we choose is in fact this situation. The second torus is bigger, then the third one is intermediate, and then the first one is smaller. But they are all growing with n. Nothing is shrinking. Scale separation is controlled by one of these parameters, and indeed you can have arbitrarily, parametrically scale separation at both weak and strong coupling because we can tune the other parameters here. Now, here I have a comment on the flip, but I think I will skip for reasons of time. Let me conclude. So, scale separation, I think, is a meaningful property to demand for string compactification or for string phenomenology. It's not the only way to go, but it's a meaningful way at least. It's a meaningful assumption. And we gave evidence, just purely from supergravity, that vacua, scale-separated vacua, if they exist, probably they are in a region with few supercharges, or something is going on with the weak gravity conjecture that we still have to understand in anti-de Sitter space. And for the second part, I think one of the lessons you can draw from these works is that probably there are more solutions we are not aware of with scale separation, at least at the supergravity level, so even the smeared level. but you have to ask for non-isotropic cases. Indeed, very recently there is a series of work going in this direction, and I think that is a very promising direction to research. So, thank you.
Thank you for a very nice talk, Nicola. Many questions. Start.
Can you quickly comment on the uplift? Okay, here I just have one slide. I mean, there are many more things to be said, but just what I wanted to, one property that we understood here is that if you try to uplift directly the smeared solution, it doesn't work because the smeared solution has a negative R7 curvature, while if you solve the equation of motion in 11D, you find positive, as Thomas was saying. And the mismatch can be explained, we explain the mismatch really with computing the correction in the back reaction. So the correction were precisely the right amount to flip the sign. So this non-trivial consistency check. It doesn't prove that it exists in general, but this is a first consistency check which could have failed, and it didn't at this level.
Thanks a lot. Thanks for the talk.
Yeah.
Yeah, how do you resolve in 11 dimensions the O6?
We don't know. Flat space is this metric. In this case, we don't know. We have a classically singular geometry. I mean,
It is related to some twisting of the tori.
which makes sense.
But if you do T-duality, you go to 8 dimensions, then you go back in 11 and mass exchange with some twisting parameter of the two flux.
Okay, I'm not sure. I'm not sure. And I think the most basic answer is that we don't know. We have a classical singular geometry.
Okay, thanks.
One more here.
Thanks for the talk. Very naive question, maybe I just missed it. In the case of the de Sitter, are you able to rule out the existence of the vacuum, or just to show that it's numerically separated?
No, I'm ruling out the effective field theory. So the vacuum is there, but it's not protected against corrections. Because I can, if the gravitational mass is vanishing, you find that the cosmological constant of your vacuum is given precisely by the gauge coupling you gain.
That's the same thing we had in ADS, right?
Yes.
Okay.
Precisely. Is the same argument with one more assumption here.
Okay.
Question? Go on, throw it.
Okay.
You can throw it. Yeah.
Thanks. One sort of possibility that was not in your list in the ADS case was 6 supercharges in 3D. Is there anything to say about that?
No, I didn't look at that, so I don't know. I don't know even if there are, well, I just really don't know.
Okay.
Do you know if there are?
There are Minkowski vacua.
Yes.
No. I mean, ADS, I don't know.
Okay.
Yeah.
Minkowski is a bit.
Yeah.
The case of Minkowski for space separation is a bit.
Yeah, of course. No, so I don't know if there are ADS vacua, but it's just in the numerology.
No.
Be interesting. Yeah, okay, thanks.
One last question. Yeah.
Oh, thanks a lot for the very nice talk. When you find those ADS vacua in type 2A, how large are the flux quanta? Like, are they really big, or are they?
Sorry, please.
How large are the flux?
You can put as large as you like. It's exactly the same.
Oh, I see. So your flux quanta are not constrained by the Tepel cancellation condition.
There is one flux quantum which is not constrained, which is playing exactly the same role as HKDs. I have 6 flux in this case, one HKD is 4 flux.
Okay, let's thank Nicola again for the very nice. So there's 2 of you giving one talk, is that correct?
Yes, that's
right. Are you next, G?
Yes.
I see you. Good. All right. So this is great. We have two people giving one talk for the last session. So many thanks to Nathan Brady and Nindya Sengupta, who are going to tell us about tadpole and moduli in type 2B on the. I'm not going to keep reading it. You can talk.
Thank you very much to the organizers for giving us this opportunity to talk. And we are going to talk about tadpole and moduli in type 2B string theory compactifications using the 1 to the 9 Landau-Ginzburg orbifold. So this is some work that we have done with our advisor, Katrin Becker. So let's go right into it. So I'll begin by setting up notation and describing the model. And towards the end of the talk, in the second half, Nathan will tell you the new results that we have found. Okay, so fluxes in string theory compactifications are important for many different reasons. The particular aspect of flux compactifications of type 2B that we are interested in is stabilizing moduli. So in DGKT back in 2005, it was shown that in massive type 2A, on a rigid Calabi-Yau, which has no complex structure moduli, fluxes and orientifold 6 planes, they can stabilize all of the moduli. So this sort of motivated Becker, Baffa, and Walcher back in 2006 to study the mirror dual setup, where you take type 2B on the mirror dual Calabi-Yau, which has no Kähler structure moduli. So they are non-geometric, because if you look at type 2B supergravity compactifications in the geometric setting, the size of the internal manifold will always show up as a Kähler structure modulus. So since we don't have any in this setup, we can safely say that the internal manifold is non-geometric in some way. So, but in string theory, we have ways of producing these things. Essentially, all you have to do is to produce an internal superconformal field theory with the appropriate central charge, which is C+9. And these models are good because since you have no Kähler moduli, you don't have to stabilize them. And all of the complex structure moduli are putatively stabilized by the flux-induced superpotential. At least that was the claim that was made by the authors of this paper. But more recently, Katrin, with her collaborators in 2022, they looked at all of the solutions that were presented in this paper, and they found out that all these solutions, all the flux vacua, they have a large number of moduli which are massless. So essentially, back in 2006, they were so confident that the flux-induced superpotential will stabilize the moduli, they didn't even bother looking at the masses of the fields. But closer look at those solutions revealed, and this paper also presented more new solutions. And in all of those solutions, there are a large number of moduli that are massless. Okay, so what do we do? Do we stop looking at the solutions altogether? No, because the two really nice properties that they have, the fact that there are no Kähler moduli, and also the non-renormalization theorem of the flux-induced superpotential, these two properties make these models still very attractive. So what one can do is to find more systematic search for solutions and try to find solutions where you can increasingly stabilize more and more moduli. The reason why this was not done back in 2005 is because the lattice of supersymmetric Dirac quantized flux backgrounds in these non-geometric Landau-Ginzburg models, they have a really large rank. So a brute force search for short vectors, by short we mean fluxes which do satisfy the tadpole cancellation condition, it is quite expensive. So the work that we have done with Katrin is that we essentially start systematizing the search for solutions in these models. Okay, so let me first give you the basic ideas. So we essentially write down string theory where C equals 15, where M4 is the non-compact space-time directions, and n is the internal SCFT, where c equals 9. Now, and n equals to Landau-Ginzburg QFT of chiral superfields is usually given by this kind of an action, where this W is the worldsheet superpotential, and this K is the Kähler potential. So there should be a comma right here that's missing. So it's believed that it flows in the infrared to a CFT provided K is chosen suitably. The worldsheet superpotential W only receives wave function renormalization. So if we choose the superpotential to be quasi-homogeneous polynomial, this can be absorbed in W as an overall scaling. For one chiral superfield with a superpotential of this form, phi to the k plus 2, where k is some integer, central charge of the infrared fixed point is given by this. And it is precisely the central charge for the k minimal model of the n equals to SCFT. So if you take, instead of one chiral superfield, if you take n of these and tensor them together, you get the total central charge to be 3 times nk over k plus 2, which equals 9 if you choose k and 9 of from this set. So 1 for k and 9 for n, or 2 and 6, 3 and 5, excuse me. Or 6 and 4. So this model goes by the name of 1 to the 9. This goes by the name 2 to the 6, 3 to the 5, and 6 to the 4. So for specificity, we'll focus on the first model, 1 to the 9, and we'll take an orbifold of this guy. So in 1 to the 9 mod Z3, we take the k equals 1 minimal model, and the worldsheet superpotential is given by the sum of the individual building blocks. And there is a diagonal Z3 symmetry in it, where each phi goes to omega times phi, where omega is a cube root of unity. So how do you count how many complex structure moduli and Kähler moduli this model has? Well, essentially, since the internal manifold here is non-geometric, you cannot simply count how many co-cycles or cycles you have. So you have to give a CFT description. So it can be shown that the chiral and antichiral superfields in these models, they have a ring structure, and the CC chiral ring given by this. So this is the ring produced by the 9 fields that you have, the ring operations plus and the operator product, modulo the partials of the superpotential going to 0, which is phi 1 squared to phi 9 squared. They count the H21N elements. So you have 84 of those. You can show that there are 84 different ones in the 1 to the 9 model. And there are no Kähler moduli because there are no non-trivial AC primaries in this model, or even when you Z3 orbifold it. So H11N is equal to 0 as well. So now, because we want n equals 1 supersymmetry in 4D, we take an orientifold. So the orientifold action is given by tracing the parity, worldsheet parity, B-type parity operator with the following holomorphic involution of the internal space, where phi 1 and phi 2 are flipped, and an overall minus sign multiplies the entire thing. And then one can compute how many of these complex structure deformations survive under the orientifold action. And you can see that there are exactly 63 monomials of the ring, which are of the form phi 1, phi I, phi j, phi k. I and j and k are not equal. And you count there are 63 different combinations of this kind. Okay. So now we have to also give a description of branes and fluxes in this non-geometric setting. Because these are not manifolds, again, you have to precisely define from the CFT perspective what do you mean by supersymmetric cycles. And it's best to look at supersymmetric cycles in this setting by looking at A and B branes and distinguishing them by the boundary conditions of the super current operators G plus minus. So you can either impose this boundary condition or that one. This is the A type and this is the B type. So in the phi space, A branes, so now we are talking about one of the building block minimal models. You can show that the A branes in the phi space are pre-images of the wall-sheet superpotential having a constant phase, which by using some R rotation, you can fix to be the positive real axis. So each building block minimal model essentially comes with these three non-compact cycles, which we call V0, V1, and V2. They are clearly related by this equation that V1 plus V0 plus V2 is 0. Now, a cohomology basis of the space of A brane charges are spanned by the RR ground states L. This is again for one building block minimal model. L goes from 1 to 2. And they are represented in the chiral ring in this fashion. So essentially, you only have 1 and 5. So there are 2 elements that generate the entire ring. The correspondence is that for each RR ground state, you essentially assign phi to the L minus 1, and with some normalization factor that we choose for convenience. And I'm suppressing it in here. So how do you calculate the Ramon-Ramon charges of the A branes? Essentially, you compute a one point disk amplitude like this, overlap, and essentially it amounts to computing a simple integral of this kind. And when you have 9 of these models tensor together, your RR ground states would be a tensor product of 9 states of this kind, and then you have to see how many of those survive this Z3 orbifolding folding and so on. And without going into more details, I'll just simply state the result that the HPQM with P plus Q is equal to 3 is given by ground states of this kind with this condition imposed, where the sum of the Li's has to be 0 mod 3. So you can either get 3 or 6 or 5, 3 or 6 or 9 or 12 or all the way up to 18, I think. Yes. You get 9, 12, 15, and 18. Hold on. I'm missing something. Yeah, if you get if you choose all the L's as 1, you get 9, and then if you take all the L's as 2, you get 18 essentially. Yeah. So those are your options, and the Hodge degrees in terms of the values of PQs, they can be identified by looking at the U1 charges of the internal n equals 2 SCFT algebra, and these are the classifications of the PQ forms. So the 3 form fluxes in the NSNS and the Ramon-Ramon sector are supported on A branes, and we complexify this in this fashion, and then the tau is the axial dilaton. And for supersymmetric Minkowski vacua, the flux has to be H in H21N. So we only look at, for this particular part of the project, we only looked at Minkowski solutions, but there also exists ADS vacua in this model. So this is one of the conditions that we impose, that the sum of the L's has to be 12. So the orbifold of the tensor also identifies brane states by summing over orbits. So essentially, you can define 3 cycles, which are tensoring the 3 cycles from the building block minimal model, but the ones that survive the orientifold action. So there is a basis of 128 3 cycles that you can define. Yes? Yes. So the A cycles, the cycles we are calling A branes, essentially. Yeah. So all right. So there are 128 different 3 cycles, independent 3 cycles in this model, and there's a basis, there's a construction of it. We don't go into the details, but on each element of the basis, you impose the Dirac quantization condition, which goes like this, and then where N and M are integers, of course. And the B branes usually you use the method of matrix factorization to construct the D-branes. And they are useful because they can support orientifold planes and other sources. And again, skipping details, we can show that the orientifold that we are considering, it has a D3 brane charge of 12 when you use the matrix factorization technology. So the tadpole cancellation condition for the models we are considering looks like this. N flux plus number of mobile D branes that you can have, D3 branes, has to be 12, where the flux tadpole is given by this formula. Okay, so there are some crucial properties of the flux tadpole that are useful in analyzing solutions. So take an arbitrary flux, which is some complex linear combination of the 63 different fluxes that you can turn on. The B's are complex numbers, and impose the Dirac quantization condition on a basis of 3 cycles. So essentially, the real and the imaginary parts of B, they get related to 126 integer variables. We call them flux quantum numbers and denote them by Y. And when you calculate the flux tadpole, the formula for which was given in the previous slide, you get this expression, where now we set the value for the axiodilaton equals to omega. So this is an order 1 string coupling. When you do this, you get 81 sum over bi squared, right? So we already know these bi's are related somehow in a linear way to these 126 integers. So when you expand this out, when you replace the variables, you find that the flux tadpole is equal to a homogeneous quadratic in 126 integer variables where all the coefficients are integers. So that essentially tells you that the values of the flux tadpole are integer. And not only that, if you take one of the bi's, assume that you only had one omega, one possible flux. For that, if you calculate 81 bi squared and do the same exercise again, replace bi by what it looks like in terms of yi and yj, you get the same behavior. You get a homogeneous quadratic with integer coefficients. So what that means is that if you really do turn on a flux, it must contribute at least 1 to the flux tadpole. So to ensure the fact that we want to satisfy the tadpole cancellation condition in flux has to be smaller than or equal to 12, it is sufficient to restrict to up to 12, what we call 12 omega solutions, in the sense that you need not turn on more than 12 different fluxes. So already in BBVW and BGWW, so this is the 2005 paper and this is the 2022 paper, solutions with smaller than equals 12 flux tadpole were found. The minimum value of the flux tadpole among those solutions is 8. So there are 2 questions that we ask in this project. One is there a flux background for which n flux is smaller than 8? And the second question is, how can we systematize to find all solutions with this bound? And in order to check how many moduli are stabilized, we need to know something about the flux-induced superpotential. Now, in the traditional geometric setting, is given by this GVW formula, where W is G wedge omega integrated over the internal manifold. Now, this continues to hold true for I think I wrote this wrong, not 2B on 3-folds. I wanted to write 2B on the Landau-Ginzburg orbifold. Now, this flux-induced superpotential does not receive any perturbative or non-perturbative corrections. So there are arguments by these authors that this formula does not receive any corrections in all orders of perturbation theory, both alpha prime and string coupling. Now, in BBVW back in 2005, they also proved that this continues to hold true for non-perturbative corrections as well, because all the relevant instantaneous that could correct it, they do not exist. So this 3-level formula for the superpotential is exact. So if we want to see how many moduli are stabilized, we can take this, the 3-level superpotential and calculate the rank of the mass matrix with it. And the other interesting feature that this has is that because we are looking at Minkowski solutions, we don't have, so essentially the condition is that W is 0, and therefore the supersymmetry condition goes to this. And because of this, we can show that the rank of the Hessian of the superpotential is exactly equal to the rank of the mass matrix. So all we have to do is to calculate the Hessian of this guy and calculate its rank. So in order to tell you all the properties of the solutions that we find, this property is going to be really important. Okay. So now Nathan will tell you systematic explorations of the solutions that we have found. Here you go.
Thank you. Hello. Oh, yeah. Can you hear me? I will assume so. Excellent. All right. Thank you, Nindo. So, like you said, I get to tell you all about the results that we found for this particular model. And there are some conditions I want to sort of recap. We have the tadpole cancellation condition. Make sure I understand. Which was stated before in the previous slides. We're looking for a physical, so when that is satisfied, we call it a physical solution. It's sufficient to restrict our search to fluxes which are below 12, which comes from that tadpole cancellation condition. Next, so restricting our search to look at fluxes which can get progressively larger. We're turning on more complex structure moduli, or more fluxes, I should say. So our search is an order by order in number of omegas turned on. So searching through all possible 12 omega configurations is obviously computationally difficult, but we present this another direction of going about it by eliminating order by order tadpoles that can't don't saturate the minimum tadpole value. So we're going to find a minimum value for this particular model. So as a crude lower bound and for the tadpole flux contribution, for the set of n omega flux backgrounds, now we're finding the best lower bound. And we find that we give a complete set for omegas up to 4, and what those lower tadpole values are. So, okay. So for the 1, 2, and 3 omega solutions, on the left here, the form of the flux appropriately normalized with the correct coefficient there for quantization. We find the minimum tadpole value for 1 omega is 27. And this is just the enumerated list of complex structure moduli that we established beforehand. There's a typo here. There should be, oh wait, that's later on here. So we find they can stabilize 16 massive scalars, or 22, depending on your choice of index, in this enumerated list. That's the rank of the mass matrix, as Nindo mentioned before. Here, like I said, this was in our enumerated list. These are the oriented fold directions. There's a typo here. There should be actually 56. But we find that its minimum tadpole value is twice as large as the one where we were not in the orientable direction, and it also stabilizes 22 scalars. In the 2 omega case, we find the minimum tadpole is 18, and they can stabilize 16, 24, or 26 for this set of index enumerated complex structure moduli. And in this set, it's 28 or 32. Next 3 omegas, we have 2 choices here. We find that its minimum contribution to the flux tadpole is 27, and it stabilizes anywhere from 16 to 46 in this set. Okay. Next is going to be, oh, did I skip it? There we go. Next is our first situation where we actually satisfy where we find that the tadpole contribution is actually satisfied. So we find the minimum flux tadpole is 12. And our first example with a physical bound, we can see that we'll have this form, which you can check explicitly and by using the equation for the flux tadpole, 81 times the sum of the coefficients squared. You can check and see, yes, you reproduce tadpole value 12. This was this also, if you include phases, you can get you can express this as a family of solutions. We found exhaustively these, and the phases, the properties of this, you can check that if this is properly quantized, then this one should also be properly quantized. The quantization condition in this situation follows this pattern, where it's the sum and difference of the appropriate phases here, and this is your quantization condition. We find that this is properly quantized if and only if this relationship of the coefficients A, B, C, and D, the sum and difference of those, modulo 3 is equal to 0. Okay, so this is an exhaustive list of that of the minimum tadpole for the 4 omega solutions, and here alpha, beta, gamma were the associated values there, the enumerated list. So we find this set stabilizes the scalars from 12, 22, and 26. Okay, moving on, out of time. So the shortest vector problem. So we actually answer this question that Danindo proposed, is are there any tadpole fluxes that are smaller than 8? And we found exhaustively that that answer is no. 8 is our minimum tadpole for this model. We do this by ruling out, as I said before, in our procedure, and so I'm going to describe the procedure now, is to rule out these by looking for specific tadpole flux values that are less than. So we turn on order by order, and this is allowed because the minimum value for a tadpole, the minimum contribution that they have is 1. So turning on 1 should at least contribute 1 to the tadpole cancellation, the tadpole flux. Okay. So choose T complex B. So 2T, set of 2T equations, non-zero, and set the remaining to 0. So we have a set of 114 real linear equations in integer flux quanta, which Danindo mentioned, we described as Y. So this set of non-zero coefficients gives us a reduced expression for that tadpole flux. And so we express it like this, where Qij is some symmetric positive definite matrix. That's what I meant. So where these CIs are arbitrary integer valued, form a integer value vector. So So now the question becomes, is this less than or equal to t for some choice of integer ci? And remember, we're setting t equals 7 in this problem. So this is computationally difficult. This can be computationally difficult in quadratic Diophantine equation. So we need some way of improving this timing. And so we actually managed to take a computation that might have taken a month to do in maybe a couple days, using parallelization techniques as well. So we define the level set. So what we're doing, now I'm going to describe this algorithm, which helped us do that. So we define a level set in R2T, which is this. And points that lie outside of this ellipsoid will have guaranteed values that are larger than our t-bound. So are there integer lattice points on LT or in its interior is the question that we ask. So we call this procedure the eigensieve method and an algorithm. And it's really just a combination of enumeration and sieving techniques. So using the eigenvalues of our symmetric coefficient matrix Q, the eigenvalues, the two t eigenvalues, which are positive and in increasing order like that, and the normalized eigenvectors, we can actually do an exhaustive search, and as opposed to an approximate technique. So we carve out a finite region in integer space using the smallest eigenvalue of that coefficient matrix. So lattice points in this region, which satisfy the magnitude of the point dotted with the corresponding eigenvector, is larger than the square root of the fixed flux tadpole value, which we set to 7, divided by the associated eigenvalue of that eigenvector. So if a point satisfies this relationship, we sieve it off. So we explicitly, so this allows us to go through a set of points, millions of points, and check this condition, and which improves calculation time significantly. So all lie outside of this, and they're sieved off. Explicit evaluation of those that remain in this reduced flux, we actually calculate this value now. Okay. So let me summarize what we did. So we initiated a systematic search for solutions with the lowest value of n flux, and we organized them by the number of flux of omegas that are turned on, order by order, and perform an exhaustive search up to 7 omegas turned on. That's what I want to say. So this is similar to this is the shortest vector problem, which is NPR, but that's unimportant. So for the lattice of supersymmetric flux vacua in this, we find that it is the minimum definitively is 8. A large class of 8 omega solutions were found, but I should mention that this is not an exhaustive list. It is, yes, it is not an exhaustive list. And I think I must have skipped over the 8 omegas, didn't I? But yeah, yes, I did. So the punchline was the 8 omegas. So we find T-min is the minimum of this. It stabilizes 14 massive scalars. The quantization condition is this, which we picked up from the 4 omegas. This gives us a set of 8 omega solutions, but it is, like I said, not exhaustive. Okay. My butterfingers. Sorry about that. Okay, so wrapping it up. Sorry about that. So all solutions that were found have a number of massive moduli below the tadpole conjecture bound. So there's no discrepancy in that. Next steps are to push this search exhaustively, hopefully to 12 omegas, and moving away, this would likely require us to move away from the symbolic computation of Mathematica. And finally, we aim to extend all our analyses to those other Gepner models that mentioned, the 2 to the 6 and so on. 2 to the, yeah. So, thank you.
Thank you, Nathan. Thank you. And yeah, that's great. We're a little late, but a couple of quick questions. 1 or 2 quick questions. Marianne.
So if I understood correctly, you need to turn on more cycles, fluxes on more cycles to lower the tadpole, which is counterintuitive.
It is, yes. So this is like the symmetry of the lattice of the supersymmetric fluxes. We don't think that we quite understand it, what's happening. So if you turn on only 1 omega, the minimum tadpole turns out to be 27. You cannot do better. But if you turn on 4, you get 12. If you turn on 8, you get 8. So we don't really know how. And the other thing is like the tadpole minimizing flux backgrounds. Those are weird in the sense that each turned on omega or flux is contributing equally. So all the solutions we have, they have this property and we don't understand why. It could have been that one guy contributes 1, the other gives it 2 and things like that, but that doesn't happen.
Andre.
I was just wondering how large your search space actually is. And if you did a 63 omega case, how large would that be, for example?
Okay, so I can give you a rough idea. So it depends on what the.
I mean, I was wondering 10 to the what?
Yeah, it depends on the value of the lowest eigenvalue that we have of the coefficient matrix.
Yeah.
So if you calculate. So say you are trying to see if there are 63 omega solutions with tadpole value of 63, let's say, right? So you have to calculate square root of 63 divided by the smallest eigenvalue. The smallest eigenvalue essentially goes to 10 to the minus 5 or 6 or something. So it's a huge, even though the region is finite.
It's 10 to the what now? I didn't follow that.
10 to the minus 6 or 7. Or something like that.
Now, how many possibilities? It should be 10 to the plus.
So that's for So that's for each direction in this lattice.
Yeah.
You have to go that far out, and then you have 126 different directions to go.
Okay.
So the finite region that you carve out, that is huge. I mean, with 7 omega solutions, we went out. The finite region we carved out, it had about 100 million or so lattice points to begin with. But then by sealing off, we brought it down to about a few thousand.
So systematic search at some point breaks down, and then you have to use heuristic search methods. So did you try any of that?
No, we only have to go all the way up to 12 omegas, not beyond. So for that, even I think the search is still very expensive. We don't have the necessary computation power. So what we are trying to do right now is to not do any symbolic computation at all and make it completely numerical and see if we can still do exhaustive searches. Because the symbolic computation is essentially what is the bottleneck with this entire search.
Okay. One more question. Yeah. This is already.
Thanks. Thanks for the nice talk. You said that in all the solutions you found, there are massless moduli left. Did I understand right?
Yes, that's right. So we have 64 moduli in this model, 63 complex structure moduli and the axial account. So when we calculate the rank of the mass matrix, it's a 64 cross 64. And then the best we could do is stabilize about 46 moduli, but the tadpole value is quite high.
Did you check if this is just a quadratic order? So is there a modular space,
or
are they lifted?
Rank of the mass matrix, right? So you are only calculating the Hessian of the superpotential. So you could actually, in principle, calculate higher order terms. So that's another aspect in which we are looking into at the moment.
Okay, thanks.
Oh, go on, one more, just mind you.
Just relatedly, these solutions are at W equals to 0 or W not non-zero?
These are all Minkowski vectors, so W is equal to 0.
Right, and I think that actually also explains the presence of non-stabilized moduli.
There also exists ADS vector in these models, but we didn't include that there.
You're eating into your coffee break, but one more. I'm happy to It's good to discuss.
Yeah, more than a question, this is a comment. It's just this reminded me of some work done some years ago on orbifold, toroidal orientifold set n and set n times set m. It was similar to this, and this reminded me because I think this 1 to the 9 model is related to some Z3 times Z3 orbifold.
Yeah, it's
so probably it can be put in the same language of these models that were considered before. I'm not sure if the Z3 times Z3 was considered, but ZNs were considered and Z2 times Z2 were considered.
Right. So the 1 to the 9 mod Z3 is like before your orientifold, it is dual to a T6 modded by Z3 cross Z3, almost like DGKT, but the Z3s here are not exactly the same as the one that DGKT considered. But these are mirror duals before you turn on the classes.
Okay, let's thank Nathan and India again. Thank you.
Let's keep the Zoom running.
Hey, just FYI, we continue at 4:30, okay?
Sorry, I'm too slow.
Bien, ¿cómo va el estrés de organizar? Todo tranquilo. Va funcionando. Me pasan estas cosas que yo no tengo más, no sé dónde están las cosas. Sí, pero salvo eso. Ahora recién fui a guardar 12 botellas de vino en mi oficina. Así que ya estamos preparados, claro, para cuando acabe festejar. Sí. Pero no, todo tranquilo. Si quieres ir al baño, dar un café. Gracias. Thank you. You're welcome.
Perfecto. Sí, lo hemos mirado con Nico, funcionaba más.
So you know it's 25 plus 5. A 3 minute, a 1 minute, and a 0 minute time.
Yeah, see. I'm worried about time, but the last part of the talk is this kind of last part of the talk that you can just say, okay, I'm this and this and that.
Yada, yada, yada. We prove the statement. Any questions?
I spent the whole time seeing what is the statement. Okay, we proved it.
Exactly. Sometimes it's like that. Okay, let's begin. This is the last session of the first day of Landscapia. I'm very happy to welcome Jose Calderon Infante from CERN, who will tell us about higher spin symmetry and infinite distance and its stringy origin.
Thanks a lot for the presentation. Thanks a lot to everybody for coming back from the coffee. And let me also thank the organizer for putting all this together and for giving me this opportunity. So I'm going to talk, this talk is going to have two fairly separated parts. The first one will be about higher spin symmetry and arguing that they are always at infinite distance. And the second one, I will rather ask about the stringy origin, where to find the string theory. So the first one will be based in this paper in collaboration with Logan Baum, and the second one will be about ongoing work with Irene Valenzuela. So let me start with some motivation. So I'm going to introduce very quickly the Swampland distance conjecture, which is very known to us. This conjecture is about the modular space of the theory as parameterized by the VEF of massless scalars. And then the conjecture says that if I start at some point here and then I go geodesically to infinite distance, I will always find a tower of states, as with infinite number of states, that will become exponentially massless as I explore the infinite distance limit. And not only this, nowadays we actually enjoy precise order 1 bounds on this parameter alpha, both in the lightest tower and also in how the species scale, which is the quantum gravity cutoff, will going to fall off. And even more, today we also enjoy a pattern that seems to connect these two things. So we are getting a lot of understanding about this conjecture. There is more progress about it. You know, we have a lot of top-down evidence, both from string theory. I can simply not cite all of the papers. So let me just put a few of them. Also in ADS-CFT, which is what I'm going to focus on. We have some proposals for bottom-up motivations, why this should be true, based on first principles. And there is connections to other conjectures. We have phenomenological implications. There is a lot of work in this conjecture, so it's something to care about. So as I was saying, I'm going to focus in the ADS-CFT side of the story. So first, I will explain how this conjecture looks in ADS-CFT. So essentially, I will try to give the exercise of taking the conjecture in ADS, and I will just translate it to the CFT. So this question was already asked in these two papers, and in particular, in this one, they put a very sharp conjecture, very well-defined conjecture. And it is about the conformal manifold of any local CFT in more than 2 dimensions. So for that, let me first explain what is the conformal manifold. The conformal manifold is nothing but the dual of the modular space. So now, instead of being parameterized by the VEF of massless scalars, it's going to be parameterized by exactly marginal couplings. These are couplings that no matter what value I give to them, the theory remains conformal, which is very non-trivial, because the theory can be very strongly coupled, still conformal. Then when I say local CFT, what I mean is that it possesses an energy momentum tensor. This is very important because that means in ADS-CFT that in the bulk I have a spin 2 graviton. So that means that I am actually talking about gravity. That gravity is dynamical. And within this framework, because d bigger than 2 is just more than 2 dimensions, these conjectures are 3 parts. The first one is that any higher spin point must be at infinite distance. What do I mean with this? So imagine I'm here at some point, and as I approach it, I find that my conformal algebra enhances to a new global symmetry, a larger one, that is a higher spin symmetry. Essentially what I get are conserved currents, as usual, but these currents are not spin 1. They have spin 2, 3, 4, 5. They have higher spins. So then this conjecture is telling us that this cannot happen in some random point of the conformal manifold, should always happen at infinite distance. This is the first part. It's called part of the conjecture. Also says the converse statement. This is that all of these infinite distance limits, they should all be higher spin points. So whenever I go to infinite distance, I should find this enhancement to a higher spin algebra. And last but not least, the third part is telling me that if I consider the anomalous dimension that is essentially measuring the mass of these higher spin fields in the ADS, it is going to go to 0 exponentially with the distance, which recovers the exponential in the distance conjecture. Okay? So then once you have this very sharp conjecture in the CFT, you can ask a very nice question, which is, can we actually prove it? Can I go to CFT, which is a very well-defined framework? Can I put my assumptions? Can I prove the conjecture? And in fact, in this paper, we combine conformal perturbation theory with higher spin symmetry for, most importantly, establish the first part. So we can really prove that any higher spin point should be at infinite distance. But not only that, for point 2, we cannot say much, but we have a finite versus infinite distance criterion that essentially takes the question, is this point infinite or finite distance, and translate it to information about the CFT data, something you can try to get constraints on. And for the third part, what we find is that as you approach a higher spin point, the alpha that appears in this exponential is encoded in a very particular 3-point function evaluated at the higher spin point, which is nice because now you can try to take theories that enjoy this higher spin symmetry. They are extremely constrained, and you can try to study this coefficient. Put bounds, see if it is non-zero, and all that. So let me stress that for this, we put no extra assumptions. So really the assumptions that we put are those of the conjecture. We impose the existence of a conformal manifold, that the theory is local, and there is more than 2 dimensions. For instance, we don't assume any supersymmetry. Supersymmetry could be required to guarantee the existence of the conformal manifold, but the proof doesn't use it. It could be underlined, but it doesn't use it. And the existence of the energy momentum tensor is very crucial. Without it, there is a particular step in which my proof will fail dramatically. So let me then give some sketch of the proof. Outside of the higher spin point is a descendant because it's essentially the divergence of J, of the higher spin current. But in the higher spin point becomes a primary. I will review a bit how this K appears. So let me just give a sketch of the proof. For those of you that have already heard like 5 times this sketch of the proof in different conferences, no worries, please pay attention because I have a slightly modified version. So the idea is that imagine that I'm in the conformal manifold, and now I take here a higher spin point and a neighborhood, and now let me consider a trajectory. So I focus in this trajectory parameterized by t. Now, what I can do is that in any of these points, I can draw the would-be tangent vector, and in the CFT, this is a marginal operator. So essentially restricting myself to a trajectory is restricting myself to a given marginal operator. And then I can apply conformal perturbation theory to write down this equation. Then I can impose conformal symmetry and finally get to this equation that essentially is telling me that as I go along this trajectory, the change in the anomalous dimension of a higher spin is related to this CJJO that is just encoding some information about this 3-point function. So far, the only thing that I have done is to take 2 pieces of the CFT data and relate them along the trajectory. Now, one could say, okay, but you are taking one trajectory, what happens if you take another one? So if I take another trajectory, I'm just taking another marginal operator, or even another one, more crazy one. So essentially what we are learning here is that this O that I'm putting here is telling me what is the trajectory that I'm considering. This is going to be very relevant later. And now, if I actually take that the 2-point function of this scalar is correctly normalized, then this is going to be the sum logic of distance that appears in the CFT distance conjecture. So you might imagine why this equation is good for testing this conjecture, because it's essentially telling me how the anomalous dimension is going to vary with the distance in a certain trajectory. So then, putting this aside, the other ingredient is, of course, an ingredient that will tell me why higher spin points are special. So I'm going to use weakly broken higher spin symmetry. What is the point? The point is that as I approach this point, I know that the divergence of the conserved current will go to 0 with some parameter that will depend on t, and the only thing that I'm going to impose is that this g goes to 0 as t approaches the higher spin point. So here I actually put in that the trajectory must approach the higher spin point. Why is this useful? Because essentially I'm just breaking asymmetry. And that means that I can take the correlators, I can expand them in a series of g, and in particular, well, let me first explain how this goes, but very sketchy. The idea is that as g goes to 0, I can take the divergence of the correlator, and then it will just spit out a g and change the j by a k just by using this equation. Since this one contains the information about CJJO and this one the information about CJKO, then it's reasonable that in the expansion, the order G will be controlled by GKO, and the same for KKO, okay? But what is the point here? The point is that, well, first of all, this is a bit more complicated, but you can check the paper to see how to do it step by step more carefully, ¿vale? But in this case, it just works. Sorry. But for this sketch of the proof, it's easy now. So the important point here is that in this expansion, all of the correlators are evaluated at the highest spin point. So that means that I enjoy higher spin symmetry, I can impose it. And if I impose it, what I can prove for you, I won't do it here, is that these two must vanish. This looks a bit scary to use higher spin symmetry, but really it's just another global symmetry. It's not even a p-form symmetry, it's not even an invertible symmetry, it's just a normal symmetry. So really this kind of cancellation is the kind of cancellation that you get in a global symmetry when the operators that you put in the correlator don't add up to zero charge. The same thing, it's just that you have to work it out. But then, as G goes to zero, one can also show that the anomalous dimension will also behave as G squared, and that means that I can prove this for you. Okay, and this is essentially the constraint that I will put now. So now, if I consider again my trajectory and I put these two constraints together, I have this kind of equation, which, by the way, is nothing but the bound proposed in the species scale in this paper, but an asymptotic version. It's not a version that holds at any point of modular space, but I can prove it rigorously as I go to a higher spin point, so asymptotically. This is important for us because if I take this kind of differential equation with this constraint and I try to solve it, I will get that gamma L will go to zero only if t goes to infinity, which means that the higher spin point is reached at infinite distance along this trajectory. And this is actually very easy to understand. This equation is telling me that gamma cannot go faster than an exponential to zero, and the exponential takes an infinite distance to go to zero, so it will take an infinite distance. But then one could say, okay, so you are restricting yourself to trajectory, and you are showing that the higher spin point is at infinite distance along that trajectory. This doesn't mean that the point is at infinite distance. So what about another trajectory? But that's fine, because remember that another trajectory is just another operator. I can just change here O to O prime, and the argument will go through for another trajectory. And for another one, same thing. So that means that what I want to say is essentially that this constraint here works for every O. And this is for any trajectory approaching the higher spin point. So I show to you that any trajectory you might think of will reach it at infinite distance. So the higher spin point is really at infinite distance. Not only that, for completeness, I can show this to you for any JL, and that means for any higher spin point. So essentially what I'm showing here, the conclusion is that all higher spin points are at infinite distance, which is the first part of the CFT distance conjecture, now proven, okay? So to put a summary, let me give the status of the conjecture so far. So as I was saying, the first part one can prove using conformal perturbation theory and higher spin symmetry. For the second one, what I can mention is that it's this CFT distance criterion that we give. If I find that this CJJO is non-vanishing, then this is a sufficient condition, but not necessary, for the point to be at finite distance. So if now you can come to me and tell me that with no higher spin symmetry, this must be true, which I don't know how to prove, then you prove the second part. But so far it's a question. For the third part, remember that actually the equation that we got was this thing as gamma L goes to zero. So if now I'm able to show that there exists a node, so there exists a trajectory, such that this thing at the higher spin point, so as I approach it, doesn't vanish, I am showing that it has to fall exponentially because I just get the equation of an exponential. Again, I cannot show it to you, but it's just an interesting question for the future. So these are very interesting questions because it will be amazing to prove the conjecture, right, in the CFT. But in the next part, I'm going to move to a more explorative question, and I will ask for the stringy nature of these higher spin points. So essentially, if I go to string theory and I build an ADS vacuum, what are these higher spin points? What makes them special? A very good question. So at the moment you have the conformal manifold, that means that actually you have an operator in process. So essentially the operator is spanning the tangent space.
Yep.
So when I say I choose an operator, I'm choosing the operator as a vector field in the conformal manifold.
Got it.
In fact, for the proof, you need that because remember that the proof was always local in the highest spin point. So in fact, I just need to do it in the highest spin point.
What breaks down if you take the spin to be 2 or 1?
For spin 1, it's clear, and it's that I cannot show the vanishing. of CJKO. It's just an example. And for string 2, we need to think about it a bit more carefully. But I think it didn't work either. But I can check it. I can check it in computation.
In that case is a little weird, and we can. I'm happy to discard that case because it means you have multiple stress tensors. It's not as nice as the other cases. It'd be nice.
No, but still, anytime you decouple, you are getting to stress tensors, right? You are decoupling a subset of the CFT, so you know that. Yeah. Okay, so then for the second part, I will go to something less rigorous, more explorative, in which I will just ask what are these high-risk pinpoints in the conformal manifold from the stringy perspective. So for that, let me take some inspiration in the emergent string conjecture that is telling us that in the distance conjecture, whenever I go to infinite distance, the tower will be either tower of KK modes, so at the compactification, or the excitations of a weakly coupled string. And for us, this is going to be very important because they have very distinct features in the sense that the KK tower has no higher spin fields, while the string does. So that means that the expectation will be that the higher spin points are in a one-to-one correspondence to a string limit. So essentially, I expect to get weakly coupled string in the conformal manifold. However, then this raises a problem because I'm telling you that I'm having a string that is becoming tensionless in ADS. And that means that in this limit, the string is quantized in a highly curved background, which is something very hard to study, or at least something that is not trivial at all. And that means that I won't be able to just go there, and study a string and give you what are the properties. So this is why I'm going to take the more explorative approach of rely on the CFT results that I can derive from the CFT, and then just try to extract clues. So funny questions. Yes.
Click string current.
Yeah, we'll go the coupling. We'll go to see.
No, but yes, but why did you deduce from in the previous slide? There.
The string will be coupled.
Yes.
Because the highest spin point is 3.
Okay.
Yeah, so essentially you get the. Yes,
Okay.
yes. Sorry,
Okay. Thanks. Okay. Thank you.
So then, as you were saying before that every infinite distance limit could be a higher spin field, are you saying that there are no KK limits or that they are always going to be accompanied by a string tower? Okay.
The conjecture is that there are not going to be any towers, and you can think about it from the noise separation. In noise separation, the JKT and all these examples is that you have flux, so it's not a continuous parameter. And with this unit, the KK falls, but the ADS falls faster. I'm asking, in the conformal manifold, I will be asking for something way more dramatic. I will be asking for an ADS that is fixed and an extra dimension that I can just tune, whatever I want. It's very dramatic.
Yeah, for example, at least in flat space, you can get in D lower than 9, you can get like string towers, but they are always accompanied by KK towers. So maybe there was something like similar here.
Kind of happening is the other way around, that we never get the KK. I will show actually an example of this.
You look at fixed, right? Fixed conformal anomaly.
In the CFT, do you look at? Yes, I think that's the point. Yeah.
It's the conformal. Yeah. It's proven that you can change the conformal.
Yes, that's right.
So then, going on, what I'm going to take is a distance conjecture approach. Because for those of you that are not used to the distance conjecture, typically if I tell you the value of alpha, so this exponential rate, you will guess the nature of the tower. So if for those of you that have worked with this, if I write these two equations, you will tell, this is a compactification, and this is a. However, if you put out a caveat, and if it seems that, like it's not that easy, and this might be not as easy as just getting the value and say what it is, let's see how. But still, let me take this philosophy that if I get different values of alpha, I expect that the tower is different. Okay? And for that, now I'm going to restrict to a very particular setup, so I'm going to restrict to 4D superconformal field theories that have single gauge group, and that furthermore admits some Lagrange. Then, in this paper, it was already computed that actually you get 3 values of alpha. This, on one hand, is surprising, on the other hand, is also surprising. Because in the CFT, it's surprising because you have really a smooth mode. You have a lot of them. And still, the ones that are Lagrange, only 3 values, which is surprising. From the string side, it's maybe even more surprising because if I take this philosophy, this suggests like having 3 different strings in ADS unless the philosophy is wrong. So then, you could say, okay, this is suggesting 3 different strings, but I have a problem, is that none of them have the 1 over the square root of 3 that I will expect here. Actually, if you play the game of trying to match this equations, you will get that they match this one with n equals 3, 4, and 6. So the compactification to 8, 9, and the dimension. So like, what's going on? And what is going on is that we just found Miguel's puzzle because he already pointed it out in the talk in Not From Landia, in Madrid. So when you have a puzzle, what are we going to do? So let's just take a step back and see how we get this value. So for instance, this one you can get it, for example, the other ones, in n equals 2 squared for UCD, okay? This one in n equals 1 squared for UCD, okay? But this one is the one that n equals 4 super means. And now we know that n equals 4 super just means it's the dual to type 2D of the specified. So at the very least, let us try to understand how this value comes and why it's not 1 over the 3. That is the value that we find in plan. So for that, I'm going to build the convex hull for the ADS 5 process 5, but first I'm going to ask how I'm doing time. Okay, good. So the idea is that I'm going to take type 2B, I'm going to compactify this here, I'm going to take this kind of rectification where I already can use normalizing on the fit. This one will control the string coupling, this one will control the high speed value, and then I can compute how they can take other forms in Planck units, and the same for the strings. And as we are used, right now, what I'm going to do is to take this information and encode it in a couple of vectors. So then I can build the convex hull condition and check that the sharpen distance conjecture seems to be violated, which is you don't like. And not only that, you find that the projection of this point here, because in the modular space of MX5 this R has 6, so I have to take this for constant. The value that you get is 1 over 2 square root of 2, which is of course not 1 over square root of 2. So you are not even reproducing the value of the series. So we are still in a mass. But this is not that weird, because in particular, this is the limit in which the radius of the string is becoming very large in your ADS. So as I was saying before, you are comprising a string in a high neutral background, so you can trust the position of this point. So what I'm going to do next is to try to replicate this exercise by n equals 4 superdynamics in the CFT, something that I can trust. So for that, first, what are the Kaluza-Saccharine towers? So the Kaluza-Saccharine towers in this particular setup are equal to these operators that obey this equation. So I can write out this. But now we have a problem. Is that there is no sharp definition for the distance in the n direction. We have a sharp definition in the formal manifold, some logical metric, but not in the direction of that. And that means that we would expect that n will increase exponentially fast with some distance, but I cannot, so what I'm going to do is to just put this as a supergravity. So at the end of the day, I won't be able to build everything, neither for the CFT or for the bulk, I will need to combine it. I will need to use all information out. Once I do this, I just recover the result because essentially imposing it, and then I go to it. The string here are the highest impulse currents, as I was saying. So then I can compute the anomalous dimension for the top expansion for the small top coupling, which is like this. So then I get this. In this case, the distance in the direction G we control with the subgroup metric. It can be computed exactly because this is of course the symmetry, and we get this. So if I put again the supergravity plus this, I get this. So now again, let's put it as 2 dots, and I get this combination, which now doesn't violate the sharpen distance conjecture, first of all. And second of all, well, let me now say this by a comparison. So a summary of the convex hull is that in ADS 5/5, we found this convex hull, and we said, okay, in this region is still valid. So at the end of the day, what we have done in equals 4 is to really take the convex hull in the ADS side in the region in which I can trust it, and the region and the CFT convex hull in the region I can trust it, and we do it together. But there is something really happening here, and it's that they do together. Nice. We don't do it in a very weird way. Actually, we're going to see now cases in which this doesn't happen. And not only this, as I was saying, now there is no violation of the sharpen distance conjecture, so one can summarize this in this video. So, furthermore, now if I project this value, of course I will recover the CFT value because I put it in. But at the end of the day, what I want to convey here is just that one can understand really that this value comes from the type BS3. It's just that you have to be careful. You don't know how to contrast it in ADS for a very tension system. So since this is the scale separation talks, let me actually now take a little detour, and I'm going to discuss a relation with this exercise that I did and scale separation. So notice that I wrote down this, and as Thomas already explained, this means automatically I have no scale separation for the CFT. So what I'm going to do is to relax this condition. So I'm going to take this condition, I'm going to relax it by putting a parameter, and from the CFT, well, first let me argue that this parameter I'm taking is just going to be a simple distance conjecture parameter for those of you that are familiar. And then in the CFT, what I'm doing is just allowing for a very weird BPS spectrum. So I'm essentially allowing for a spectrum of BPS operators that as I take the larger limit, the first BPS operator is higher and higher at the junction. This is something that doesn't happen in the protocol superterm, but I want to play the exercise to see what I get. And for those of you that are more into modular stabilization, actually what I'm changing is the S5 stabilization. I'm changing how the vacuum, the modulus S5 talks to the ADS scale. If I do this, long story short, I will just take the CFT, I will just take the ADS, I will take the regime validity, and I will glue together the convex halves. And then if I allow beta to be bigger than 1/2, which is anti-scale separation, in the sense that the Kaluza-Klein tower is not the ADS scale, but it's lower, not higher, so it's not the scale separation we want, then I will get this. So, as you can see here, there are two things. First, the convex half doesn't glue together nicely anymore. And actually, this seems a bit pathological because if I tune the direction, there seems to be some kind of discontinuity here. So they don't seem to agree, the ADS and the CFT. And furthermore, one finds that violation of the sharper distance conjecture from the CFT very dead. What if I do the same, but now for a scale separation? Now I take beta to be smaller than half, and then I have to include the string because it's becoming relevant, or it was not relevant, and I find essentially the same. Now what I find is that again, the convex halves don't glue together with what is quite pathological. And second, that I again find a violation of the sharper, but now it's in the bulk. And because it's in the bulk, now I have to give a big of a caveat, because notice that the violation is in the regime in which the string is not in the highly curved ADS, but it's in a highly curved S5. So they want to worry about the quantization of this string, whether this will be in control or not. I will say it is because maybe the S5 modes are very weird, but the ones that propagate in the ADS probably will only see the ADS, which is really curved. But okay, one can
This equation is equivalent to take an orbifold of the S5.
You don't get a space variation if you take a orbifold of the S5. Notice that I'm doing something way more dramatic. I'm not only taking the KK scale and pushing it by another one. I am really changing the parametrics, how they scale in the larger limit. This is something that as Thomas was explaining, this is bizarre in the CFT. This looks very, very bizarre. So yeah, but all in all, the message that I want to convey is that even though this is just some kind of game that I just played, it kind of suggests some link between this sharp and distance conjecture. You have a conformal manifold and no scale separation. Because notice that the moment I break it, everything breaks down. Okay? So let me now continue with the purpose of the talk. What about the others? I explained that the one with the square root of 2 seems to be the integrate that to be a string. That's okay. But what about them? So this one okay, this one are these new strings, as I suggested in a previous slide, or is it the same string but in weirder patterns? This is the question we can ask. So at least what I can say is that they will have very different elements. Why? Because one can take the equation in this paper for alpha, and one can rewrite it in terms of only A over C, which are the two central charges of a whole CFT. And this in ADS-CFT is known to be relevant for various aspects of the low energy effective theory that is related to ADS. For instance, a very nice result is that if A is different from C and large N, there is no weakly coupled the description of low energy. And that automatically means that for these two values, this will not have an Einstein weakly coupled Einstein low energy. So for instance, a way of explaining this to yourself physically is that in this n equals to superconformal QCD, which is this case, this author demonstrated that there were BPS higher spin operators. So this means, you can just check it, that there is no higher spin gap. That means that at any point in the modular space, I will have higher spin line fields that will completely break my Einstein gap. And then one can actually take this equation, use these three values to take the three values that you have for A over C, because for the three values, you only three values, and then one can ask whether there is any special about these values. I don't know, maybe yes, maybe no, so far it's just food for thought. And to finish very, very quickly, let me just point out of a candidate for one of these new schools from the top down, and is that in this setup, you have just a S5 of SLK, and the SLK is an S1 of before singularity. And then there is a very particular limit that is only driven by axioms, that is a limit that you will typically consider to be a finite distance. But then you go to the CFT, and the CFT predicts infinite distance and higher speed, so the CFT distance conjecture. And then you can ask what is the string geology of these higher strings from the bottom. And you see that because of the limit you're taking and not explaining it with Rasmus, the fundamental string remains tension. So it cannot be the fundamental string, but it will be the one that is giving the higher string modes. However, one can check that if you take a D3 brane and you wrap it in the blue of cycles of the singularity, it does become tensionless. And it is a BPS string whose tension you can really grasp. But you know, this is a string that is living only in negative 5 + 1. So this is a fundamentally 6-dimensional string. So, I mean, I don't know, but looking at this set of states, I would say that this is a very interesting candidate for a new emerging string in ADS, one that would not be very straightforwardly related to our typical IoT. So to finish with some conclusion, let me just say that there is much to learn about the distance projection in ADS-CFT. This is a very interesting direction. Not only about it, but also from it. For instance, in the CFT side, one would say, what about the rest of the CFT projection? We will prove it. What about B = 2? I didn't say anything about B = 2. The second is very different, but one can try also to understand it. Can you define a distance in the central subdirection? Because I said that this is what I was missing in order to get everything from the CFT. It would be nice to have it. And from the stringy side, one can ask whether there really exists near strings in the S, in the Groovy, let's give some clues. What makes different strings with different alpha different, what are different microscopically? And what about these D3 branes trapping to cycles of the blowers in the S? Are they really strings that will give me an infinite amount of high spin port, high spin fields, is something different? Okay, that's it. Thank you for your attention.
Okay, thanks for a very nice talk. Questions?
So I have 2 questions. So when you, in the first part, when you derived this bound, and that was valid for all the OPE coefficients, I was wondering if this is useful to somehow like classify or like, yeah, see which CFTs are indeed like consistent, whether this can be seen as a consistency requirement, or does it on the CFT side not give any further insight?
I mean, it's something that it's just happens for any CFT that has an stress energy tensor and is approaching a higher spin zone. So I don't know, I mean, like, it's a constraint of CFTs, but in the sense that I can deny it. So I'm just imposing that the CFT has a stress energy tensor, I'm imposing high spin symmetry, I get the result.
Okay. And then when we were talking about ADS5 process 5, I was wondering, I got the impression that you changed the scalar fields, like only the scalar fields, but of course then you run into the issue that you will not end up in a vacuum if you do not change the flux. So I was wondering whether you take that into account, and like maybe a related comment is that last week we had a paper that has a proposal of doing these kind of things with vacuums. So.
Yeah, I'm taking a totally different perspective. Rather, what I'm doing is just to say, okay, I have to do 2 ADS backward, I can put a D3 brane, changing the flux, and then will give me some solution. Some running solution from one to the other. Or for instance, I can even do something else. We know that the ADS5 process 5 is the mean horizon limit of the supergravity solution for a stack of D3 branes. So now you can just flow the difference. And this will give you something that is conjectured to be an RG flow in the CFT, there are things one can say, and I take in this other perspective, which I don't want to include any other kind of fields. I want to stay there, and I will just want to follow some kind of flow and compute the distance as given by the KT10, and then one could ask what happens with the potential, maybe the potential should be entered the distance. That is something.
Yeah, so you need the D3 branes basically, in that sense.
Yes, and then you have to follow, go to the area.
Okay.
Questions?
Thanks. Could you say a bit more about the D3 branes that become tensionless? Like, why are they becoming tensionless? Is it because the 2 cycle is going to 0 or something? Or?
No, the 2 cycle is stabilized already at 0. The cycle is 0 volume.
Okay.
But then I have the contribution from the B field and the C field.
Okay.
So actually I have the B field and the C field integrated in the blower. They give you the action, and only when I take them to 0, these D3 become tensionless.
Okay. Okay. Are these related to little string theories?
Not sure. What I know is that in the flat space case, so if I take the orbifold not in ADS5 process 5, but the orbifold to the flat space case, these strings are known to be non-critical and give you only a finite number of states.
Yeah.
But I don't remember if they give you a gauge enhancement or a ether string. That I don't remember.
Do you know if you get like infinite many states because you get infinitely many orbifold singularities, or because you get?
The orbifold singularities are fixed. I'm taking K. This K here
okay.
is fixed. Yeah, it should be something more along the lines of what happens in equal for superjump, that you are taking the D3 brane, the work volume, you're quantizing it in a strongly curved regime, and this should dramatically change the quantization for flat space in such a way that you actually get a number of it. It should change dramatically.
Thanks.
That's the same. I was wondering if this emergent string could be a dual regime of the regime in which the vacuum energy of AES go to zero and in which there should appear a tower of states.
If you translate the CFT, that shouldn't happen because I'm moving in the conformal manifold, and there are theorems telling me that the central charge in the conformal manifold doesn't change. And the central charge is measuring for me the ADS scale in Planck units, and that means that the ADS scale in Planck units is fixed in any limit I'm taking. So this is something should not happen, at least given this CFT.
But you're going maybe in the regime in which the sphere become.
No, the sphere is white. I'm not changing that.
Okay.
The sphere is all white. Rather, you should think about these deformations really as taking the B and the C fields, integrated on the blowups, and this is an axiom that I can change. This is what I'm changing, this axiom. In fact, this is going outside of the orbifold point. The orbifold point is only if the integral of B is 1 over k. Exactly 1 over k. So whenever I change this, I go out from the orbifold point, so my string theory construction is not valid anymore.
Okay, thanks.
I had one question. In this last part where you were doing the sort of trying to model of n equals 4 theories where the KK spectrum looks different, did you prove that if the BPS states all scale with n, I'm wondering what kind of assumptions you made in this toy model. Did you sort of rule out exotic theories with that property? Did you do something short of that, but prove something within some set of assumptions? Like, how am I supposed to view this result?
So essentially, really what I'm doing is allowing for scale separation in equal 4, I'm forcing it, so allowing this kind of weird spectrum of these PS operators, and I'm not ruling it out. What I'm finding is that it will be in clash with the sharpened distance conjecture. Now one could try to make modifications, and if I, for instance, notice that, like, in this case, as I said, one should worry about this caveat here. In the other one, the violation is in the CFT, I trust the CFT.
Thanks.
Two towers, you only see the upper ones when you're in ADS, and the higher speed tower ones you move to the CFT regime.
You don't see them from like the other side, or do you?
You see them, it's not just you don't control them. So from the point of view of the ADS, I have here the string. But what should happen is that as the string becomes tensionless, this dot should not be valid anymore. It should slide.
Yeah, that's what I mean. That if like the higher spin point from the CFT region was there when you're moving in the direction of the string, your lighter tower would be like the higher spin one.
Yes. In fact, something that is kind of bothering of all these models is to notice that in that direction the KK tower is white.
Yeah.
So I don't get a string with the KK tower coming together at all. It's changed completely maybe.
Okay, thanks.
Any further questions? Okay, let's thank Jose again.